Hello everyone, I'm Tong, and this video is for Northwestern University 2023 for Physics 465 Nonlinear Dynamics, and my topic is about network concepts in Feynman diagrams. Feynman diagrams is a useful tool to do perturbative calculation of high energy scattering, which in its one of the most complicated form can be proton-proton collision at 7 tera-electronvolts in CMS, which can produce more than 100 charged particles. And for the simpler example, we can, for example, this is the electron-positron annihilation into a pair of muon and anti-muon, and which can be represented by a single tree-like Feynman diagrams. And for such kind of specific process, we typically fix the initial and the final state, which means that the external lines and are fixed. For example, in the diagram, we can see that the two initial lines stand for electron and positron, and the final line stands for muon and anti-muon. And this can be interpreted as a pair of electron-positron annihilates into a virtual photon, and this virtual photon then produce a pair of muon and anti-muon. And in the language of high energy physics, Feynman diagrams are typically constructed via a set of Feynman rules, and each kind of diagram component stands for a certain algebraic stuff. And we can see that the concepts of networks are naturally built in the construction of Feynman diagrams. For example, we can see that the fermion links are directed, which is used to distinguish the fermion and anti-fermion. And the photon links are undirected because we don't because the photon and anti-photon are actually the same thing. And the degree of a node is determined by the theory itself. For example, in the quantum electrodynamics, in the QED vertex, we must have in degree and one out degree of the same flavor, and one undirected degree for the photon. So using this kind of diagrammatic rules, we can actually construct the tree-level 2-to-2 diagram. And such diagram for this process is uniquely fixed by these rules. And we can also introduce self-loops. For example, these are 3 of the next order Feynman diagrams contributing to the previous process. And when we see loops in a Feynman diagram, it actually means that this process is higher order. Because when you increase the number of loops, we inevitably increase the number of nodes, and each node will rise the perturbative order by a coupling constant, which is much smaller than 1. So this means that actually this process have a much smaller possibility. And previously, we only introduced some traditional Feynman diagram calculation, which in the language of network is actually study such kind of ultra small scale network. And the calculation is very trivial. And the state of art of this field is actually to understand large diagrams. And in the language of network, it can be the understanding the large scale network. And the calculation is usually extremely hard. For example, a 4-gluon process, GG to GG, can have 4 different diagrams at tree level. And 5-gluon process can have 25. And the number of different diagrams increase crazily when the number of external line grows. For example, a typical 8-gluon process can have millions of different diagrams. So one of the techniques to do this kind of calculation is called BCFW recursion relation, which is actually build large diagrams from small pieces and use recursion relation to simplify the calculation. So this is doable. This is doable because in a certain kind of theory, the kind of nodes are actually fixed, and the degree is also fixed, not too small and not too big. So actually, we can use such kind of cut and paste process to classify all of these diagrams. So thank you for your listening.